All right, so in this video, we're continuing on and we're going to talk about how to actually interpret p-values. Well, what's a p-value? Well, the p-value of a test is the probability of getting evidence for the alternative hypothesis, H sub A, as strong or stronger than the observed evidence when the null hypothesis is true. Okay, so what all does that mean? So let's talk a little bit about p-values. Small p-values give convincing evidence for the alternative because this is saying that the observed result is unlikely to occur when the null is true. Larger p-values fail to give convincing evidence for the alternative because they say that the observed result is likely to occur by chance alone when the null is true. So earlier in the course, we talked about 5% being kind of like the general dividing line between significant and not significant results. So if a probability of something occurring was less than 5%, that was significant because the probability of it actually occurring is so low. So let's look at an example for how to walk through some of this. So the National Institute of Health recommends a calcium intake of 1,300 milligrams per day for teenagers. The NIH is concerned that teenagers aren't getting enough calcium on average. Is this true? So researchers decide to perform a test of null where the mean is 1,300 against the alternative where the mean is less than 1,300, where mu is the population mean daily calcium intake for teenagers. They ask a random sample of 20 teens to record their food and drink consumption for one day. The researchers then compute the calcium intake for each teen. Data analysis reveals that X bar, or the average for the sample, is 1,198 milligrams. Standard deviation is 411 milligrams. And research performed a significance test and obtained a p-value of 0.1405. So first we want to explain what it would mean for the null hypothesis to be true in this setting. So if the null mu equals 1,300 were true, then the mean daily calcium intake in the population of teens is 1,300 milligrams. Okay. State the evidence for the alternative hypothesis. So the evidence is what we get from our sample. In the sample, so for HA, is that X bar equals 1,198, which is less than 1,300. Okay, so we have some evidence because we got a sample where the average of the sample is less than the claimed average for the population. So that's some evidence. We're eventually going to want to know, is that convincing evidence? So this is where the p-value comes in, and the p-value tells us the probability of getting a result as extreme or more extreme than what we got if the null were true. So what's the chance of getting a sample mean of 1,198 if the true mean is really 1,300? The p-value says that that's about a 14% chance. So I'm going to actually type this one out to interpret the p-value, but this is basically how we want to do this, assuming that the population mean daily calcium intake for teens is 1,300 milligrams. there is a 0.1405 probability of getting a sample mean of 1,198 milligrams or less. I'm putting it in capitals just to emphasize it. You don't have to do it like that whenever you're doing this in practice. By chance alone, in a random sample of 20 teens. Okay, so a couple things here. Um, the p-value is assuming that the null is true. So assuming the population mean daily calcium intake for teens is 1,300 milligrams. There is a blank probability, so a 0.1405 probability of getting a sample mean, in this case, of 1,198 or less, because we have a one-sided alternative. It's strictly less than 1,300 based on how they set it up. So that or less is important because this is the p-value tells us the probability of getting a result as extreme or more than what we got. So it's not just the probability of getting 1,198 as the mean for the sample, but of getting that or less by chance alone in random samples of 20 teens. So this is only valid for random samples of the same size. Okay, so a couple things to note here. The p-value is the probability of evidence for the alternative as strong or stronger than the observed result, given that the null is true. In other words, the p-value is a conditional probability. So for this example that we just did here, the p-value is equal to the probability that x bar is less than 1,198, given that the population mean is 1,300. Okay, so that's 0.1405. You don't really ever have to write it as a conditional probability. You don't need to remember this or anything like that. But sometimes it helps to understand the p-value as a conditional probability of getting the result that we got or more extreme given the null is true. Okay, so if we look at the graph here, this is a one-sided test. And if the true mean is 1,300, we got a result of 1198. And so the probability of getting something 1198 or less is 0.1405. And we would say that's not statistically significant. So that's basically plausible that that could happen if the true mean were still 1,300. All right. Now, if we go back to the example where we had the pineapples, okay, that was a two-sided test where the parameter was not equal to the null value. So we could say that the values of the sample statistic could be less than or greater than the null value, and either way would give convincing evidence for the alternative. So in this example, we were testing the null that mu was equal to 31 versus the alternative that mu was not equal to 31. So we're looking for evidence in either direction. We got a sample mean of 31.935, okay, which is 0.935 greater than, so that's 0.935 greater than the mean. And so because we're looking for evidence in either direction, we have to go 0.931 in either direction, okay, if we're looking at the graph. And then the probability is the right tail and the left tail, so the p-value was 0.008. And again, if we stated this as a conditional probability, the p-value is the probability that x bar is not equal to 31.95935, given that mu is equal to 31. Okay? So that's it for this section. We're going to continue on in the next video to wrap it up and talk about making some conclusions.